Thank you. All right, well, good day, everybody. Very excited to be joined by both Nell Burns and Gordon Ashby from Bonneville Power Administration, or BPA. The focus of today's call will look at BPA's technology, innovation, research and development, implementation, and all things thereof. Nell will be presenting on how BPA's technology innovation team works within BPA's strategic planning framework to select R&D projects that benefit the agency and help achieve its strategic goals and objectives. And then Gordon will highlight a few hydro projects that have gone on to make very positive impacts for the FCRPS, in other words, the Federal Columbia River Power System. Looking at bios, Nell is the Technology Innovation Program Manager at BPA, specializing in project management of R&D for the power generating assets team. Before making the switch to R&D, she worked in energy efficiency, managing various programs for utilities in the Pacific Northwest. Gordon is responsible for the analysis and development of the FCRPS Strategic Asset Management Plan, as well as the economic analysis of capital investments in the hydro system. He received his BSc in economics from the University of Oregon and a master's in science, specialty finance from the University of Portland. In terms of framework here for the call, we've got, I guess, the next 55 minutes blocked off. We've got a great attendance, so thank you all for your participation. We're going to allocate the next 40 some odd minutes to Nell and Gordon, who are going to walk us through the overview that I described earlier. If you do have thoughts and questions that arise throughout, we invite you to use the Teams chat. So feel free to leverage that tool, not to lose those important thoughts, and we'll take them with about 15-20 minutes left in the call in order of entry, and then over and above, throw it wide open for general Q&A and discussion. So with all that said, very excited to have Nell and Gordon with us here. So Nell, please take it away.
Thanks, Chris. Okay, I'm going to share my screen and then get the presentation up. 1 second. See that? And then... Okay, is everyone seeing the first slide?
Looking good.
Okay, perfect. Thank you. Good morning and welcome, everyone. My name is Nell Burns. I'm the Technology Innovation Program Manager at BPA. I'm here with Gordon Ashby, BPA's Generating Asset Strategy Manager. Today, we're going to present on BPA's technology innovation strategy and implementation, and then highlight a few hydropower projects that Gordon's team supports. I'll talk about how BPA structures their R&D efforts, and Gordon will go over the specific projects. I'll start off with a bit of background. BPA's Technology Innovation Office serves as the centralized point for research, development, and deployment at BPA. We work with BPA managers and subject matter experts to facilitate the development and implementation of technology-based solutions. We have close working relationships with industry experts such as EPRI, CIADI, and the national labs. We leverage these relationships to connect internal SMEs with R&D opportunities or present BPA's R&D needs to the appropriate parties to help fill a gap or explore a new technology. TI helps coordinate with the appropriate parties to turn ideas into scopes and scopes into projects. We lead the process of getting the necessary approvals in place and complete a wide variety of project management functions tailored to the project's needs. We document and store all necessary project information, track milestones, and report on project progress. Technology Innovation's current portfolio is made up of approximately 50 projects and memberships with 12 industry partners. BPA's Technology Innovation Department is currently comprised of 5 employees, and we serve BPA's power, transmission, and corporate business lines. So, as you can imagine, there are more requests than the team has bandwidth to fill. To help focus our efforts and equitably distribute resources, the team develops research priorities, which are a set of topics that help fulfill BPA policy obligations, help target R&D activities, and guide the annual portfolio selection process. For 2026, the research priorities have been designed to identify gaps in knowledge, practice, or technology, provide a cost, complexity, time, or risk savings to BPA, and align with BPA administration and Department of Energy strategy. Every 2 years, the technology innovation team uses a bottom-up business approach to determine the next set of research priorities. This allows the team to get feedback and ideas from the same people who are engaging on the R&D projects. We have found this to be critical to the success of the program. TI-sponsored projects are not often included in employees' core work, and we want to take as many steps as possible to keep the SMEs engaged. We start at the beginning of the fiscal year and send out an interest request to all existing SME partners and their managers to determine a pool of internal stakeholders willing to engage and provide input. The team meets with this group to understand their R&D focus areas for the next 5 to 7 years and their initial ideas about project topics that would support their goals. This is considered a brainstorming session, so no topics are off limits. The TI team then compiles the SME feedback, organizes the inputs, and completes analysis to identify commonalities and trends. This rolls up into a set of draft priorities. We provide the draft priorities back to SMEs for review and feedback. Once complete, the team looks at the existing partnerships and programs to see where we can leverage industry-wide R&D opportunities to support the draft priorities. We then rank the priorities by leveraged resources to make our R&D investments impactful and dollars stretch. The team provides the information to executives for review and input. The executives are asked to provide their top 3 choices based on the information provided. TI uses executive input to finalize the priorities. The top 3 become the final priorities for each business line: power, transmission, and corporate. I'll quickly run through the research priorities for 2026 and their goals. The information is available on BPA's external website if folks are interested in reviewing after the presentation. I'll put a link in the chat. Under agency-wide, we have advanced analytics and informed decision support with the goal to use data analytics and augmented intelligence to optimize business planning and operations. Next, we have modernized planning reforms and efficiencies with the goal to reform framework and modeling capabilities and strengthen real-time system monitoring and forecasting. And then we have safety, security, and regulation with the goal to explore technologies and solutions that ensure best practices in compliance, safety, and threat resilience for BPA workers and systems. For power, we have generation asset management with the goal to explore technologies and methodologies that enhance risk-based decision-making to maximize asset value and preserve the reliability and resilience of assets. And then we have hydropower reliability and life extension with the goal to extend the lifespan of FCRPS assets through advanced technologies. Finally, for power, we have energy conservation emerging technologies with the goal to explore innovative high-efficiency equipment and smart building design across the residential, commercial, and industrial sectors. Then last but not least, we have the transmission priorities. We'll start with transmission asset management with the goal to standardize and modernize asset health metrics and asset management best practices. We have transmission resiliency and reliability with the goal to explore the use of technologies and advanced digital platforms to support proactive, data-informed decisions that enhance grid resilience, optimize system assets, and reinforce BPA's commitment to deliver reliable, affordable energy. And grid operations with the goal to explore modeling and technologies that support reliable, efficient, and cost-effective operations. So once the research priorities are set, the technology innovation team selects projects and partnerships for the fiscal year. BPA uses a truncated version of NASA's technology readiness levels and as a criteria for project selection. The team focuses on proposals with technology readiness levels 5 through 8. We found that focusing on projects that fall in this zone to provide a higher cost-benefit ratio and make our investments more impactful for BPA. Projects where the goal is to test a technology to see if it meets BPA's needs are grouped in TRLs 5 and 6. Projects where the goal is to ensure that the technologies work in relevant applications for BPA are grouped in TRLs 6 and 7. And projects where the goal is to ensure the technologies work on BPA's system are technology readiness level 8. The team tracks the starting TRL for each project and reports if the TRL changes based on the TI-sponsored work. While it isn't a portfolio health criteria, it does let TI report on technology progress using a standardized metric, which is helpful for managers and executives. And here are some of the current partners TI is working with on R&D initiatives and projects. We have the Army Corps of Engineers, CIADI, Pacific Northwest National Lab, the Grid Deployment Office from the Department of Energy, EPRI, NREL, Bureau of Reclamation, Savannah River National Lab, and Oak Ridge National Lab. So that concludes my brief overview of BPA's R&D portfolio selection strategy. I'm happy to answer questions at the end of the presentation, and I'm available to meet one-on-one if anyone's interested in additional details. Next, I'll pass it to Gordon to talk about a few technology innovation-sponsored R&D projects. Here you go, Gordon.
Thanks, Nell. Let's go to the next slide. And yeah, so just a little background on the FCRPS, or Federal Columbia River Power System, as Chris mentioned at the top there. So if you don't know, we have a bit of a unique relationship up here in the Pacific Northwest, where Bonneville Power funds the capital and O&M programs of the Army Corps of Engineers and Bureau of Reclamation. So BPA has no dams that we own. We fund the O&M and the capital, and they are operated by the Corps and Reclamation. So you can see where some of those dams are located across Washington, Oregon, and Montana, and Idaho in the right there. And then just there's some stats there. We've been doing this direct funding of this program since the 90s. There's 31 federal facilities across the Columbia River Basin, along the Snake River, Willamette River, several other areas. Quite a bit of generation capacity, 22,500 megawatts, about 70,000 gigawatt hours of average annual generation. And the average value of that spot market's about 3.5 billion if you were to value that way. And on average, that's about 65% of the region's hydro capacity. Go to the next slide. We can talk about some of the projects we funded through TI. So this is one of the ones that we've been working on for quite a while. We've done actually a couple projects through TI as the Shuffled Complex Evolutionary Turbine Optimization Model, or SCE-TOM. Basically what this model is something we've partnered with the Army Corps of Engineers to develop through the Hydroelectric Design Center, and specifically the Hydropower Analysis Center, HAC. What that model is doing is basically saying, given a head and flow and a number of units available and specific turbine designs, how much can you generate in a given hour? Essentially, it's an hourly model. It deploys the units the most efficiently it can, essentially. And there's a lot of benefits to that. It's become a very critical part of our capital investment analyses. So we use it to evaluate different turbine designs, different, to see if, Kaplan versus fixed blades make more sense economically and technically. And also we use it just to understand the impacts of unit outages. So I'll talk about that a little bit more. This specific project that we're working on right now is to actually improve the kind of the computational power, I guess. Because what it's doing is kind of looking at every single combination, maybe not every single combination, but it's looking at a bunch of different combinations of how you could deploy units under certain conditions. It can take a long time if there's multiple unit families and a lot of units at a plant. So like Chief Joseph Dam, for example, has 27 units. There's a lot of different combinations that those units can be deployed. And so I think when those were first being run, some of those large combination plants could take up to a month or something to finish, or some were so long that we didn't even think it was really feasible. So we have found ways to rewrite that algorithm in different languages and make it more user-friendly with the user interface. And so this is trying to enable this for more plants, make it run more smoothly, and make it so that folks that don't directly use programming languages can actually run the model as well. Let's go to the next slide now, and I'll talk through a little bit more of how this actually works and what it is, just in case you're interested. So basically, it's all based on these power hills. And so what it's doing, as I mentioned before, is it's looking at combinations of flow and head. So you can see flow on the y-axis there and head on the x-axis. And each one of those bands is an amount of generation. So at the very top line, it's a little bit hard to see, but that's 400 megawatts, for example. And you can see that you can hit it at a number of different, across the different head range there. But, the amount of flow obviously differs based on the head. So this is basically just creating a giant lookup table that says, given a flow and head combination, what is the most efficient way to deploy the units? And so kind of in the background, given which units are available, it's able to track, which way it would be deployed. So the way that we can then kind of use that, if you go to the next slide, is we can look at the impacts of having units out of service, for example. So one way to kind of look at this, and I tried to make it a little bit easier to see here, is on the top chart, if you have all units available, at the very top right, the kind of maximum you could possibly achieve would be 2,900 megawatts, for example. But if you look at what it would look like with 3 units out, that 2,900 megawatts just isn't even on that hill chart anymore. So then maybe looking at the next line where I've marked the 2,500 megawatts, you can see that you can meet that with all units available, all the way to about the middle of the head range there between the 90 and 110. But then with 3 units out, obviously you won't be able to meet that as frequently, and you have to have relatively high head and high flow in order to meet that. And it kind of goes vertical, pretty close to the right side of that chart there. So what's useful with this is we can actually get a really good picture under different circumstances of how much a plant can generate, and then that really enables us to get a really good look at what the risk of losing units due to forced outage would be. So this is something that we are really motivated to improve our ability to capture. Almost 10 years ago is when we started thinking about how to deal with this problem, because we had mostly models that were kind of based on monthly averages, and they had some shaping, but they really just sort of compared the nameplate capacity and just said, if you were to lose a unit, you'd lose its nameplate capacity. But it's often, with the Columbia River plant specifically, a lot more complicated than that because the flows vary so much from year to year. So with this, we're actually able to capture the individual unit deployments and then be able to see, even without spill, we can see that there are impacts to generation just due to the plant being deployed less efficiently when you have less units available, for example. So we're able to really kind of understand better with this model what the impacts of unit outages are, which has become critical to how we analyze our capital investments. So let's go to the next slide, and we can kind of show how the SE-TOM kind of fits into our broader economic analysis process. So on the BPA side, we run a reliability model that looks at and simulates unit availability. We do it on an hourly time step for something like 50 years to look at the full life of a unit. That model is availability workbench, something that is a commercial product. We just use that to look at the planned outages due to just general maintenance or capital investments, and then it simulates outages with failure curves that are loaded into it, Weibull curves. So from that, what we get is 1,000 iterations of unit availabilities by hour, essentially, and then that is what SE-TOM and another related model use to then kind of tell us, here's what you can generate under different investment strategies, essentially. So we run different investment strategies through the reliability model that tells us what, which units are going to be available. And then given that unit availability paired with the head and flow information and other hydrology, SE-TOM can tell us, well, here's how those units would be deployed. And then the kind of additional model called the energy linking model and kind of tells us, well, here's the actual amount of energy that you'd be able to generate under these scenarios. And it also, we can understand reserve potential as well and different unit starts and stops. And so we're able to really evaluate under different combinations of turbine design. If we want to look at combination of fixed and adjustable units, for example, what those impacts might be. Let's see, let's go to the next slide. And then lastly, for the sort of, what this all kind of comes down to is we can take the availability forecasts from different investment alternatives, for example, as you can kind of see on that left side there, and then turn it into a stochastic analysis. So we can present to executives, customers, et cetera, the range of uncertainty that is inherent to investment in hydropower, just because of the variance in energy price forecasts, water, all this kind of stuff. And so it's helpful to be able to show that range of uncertainty because just using point estimates, sometimes it's hard to understand if you're right on the line between a positive or negative investment, or do you have a wide range of certainty or of uncertainty, or are you fairly certain in the benefits? So we're able to kind of show what those expectations are, and it's been really helpful from getting buy-in, especially for very, very large projects and powerhouse modernizations. Let's see, just a couple things in the chat here. I see, is BPA able to use machine rating curves to validate the SE-TOM ensemble models? And yeah, we do some validation. I know what the Corps has done is look at the actual generation over the course of history, and then compare that to what's coming out of the model to show exactly or to compare what the model is showing, how they would have generated and deployed versus how the plant was actually deployed. There's obviously some variation there because the model is going to deploy everything exactly perfectly, I guess, which might not happen in real time. But that's one of the ways that they've looked at doing some of that. And then, can you share the average annual budget for these activities? Nell, that would be on your side, I think, right? What is the average annual budget that we're doing for power these days?
Our total R&D budget is a little over 2 million, and we split that between power, transmission, and agency-wide goals. So I think on average, your group is getting around maybe 300 to 500,000 for power projects.
Okay. All right, let's go to the next project. Next slide. So the next one we've been working with the Army Corps on is a reliability-centered maintenance pilot. And this has been kind of a partnership with the Army Corps and Aladon, who has been facilitating a lot of the pilot activities. And really the main purpose here is just to start to understand how can the Corps implement more RCM procedures in their maintenance program. You know, what they want to do is identify for specific asset types, what's the right level of maintenance to meet the reliability needs at that plant for that asset type is really the big thing. So there have been some interesting recommendations that have come out of that. There've been a couple pilots that have been complete, and there's a couple more planned in the future. So let's go to the next slide, and I'll just show a little bit more information there about the types of things that have been kind of learned. I guess that's the next slide. Let's stay on this one. So,
sorry.
No, sorry, I was rambling. Go to the next one. You were good.
Okay, go.
So just generally, what is RCM? I mean, the main focus, here's kind of the 8 questions of RCM3, but the main thing is you want to look at the specific assets you have and look at their requirements and then determine, you know, what are the right things to do to maintain this particular asset in order to meet its requirements and to meet its mission. So what must be done to reduce intolerable risk to a tolerable level, and what can be done to reduce the tolerable risk in a cost-effective way. So these are the kinds of questions that the teams are kind of going through. They're evaluating the failure modes and effects. They're evaluating the consequences of those effects, and then, you know, determining, looking at their job plans and deciding, you know, are there things that are redundant in these job plans that are primarily time-based maintenance in the past, or are there things that are lacking? And we've actually seen a few different examples. So let's go to the next slide. So the first thing I think that was looked at was the unwatering and drainage pump system. And that was one where they had identified that there were some redundant maintenance tasks performed by multiple crews. So they were actually able to reduce wrench time on that equipment at that plant. So they were able to see that effectively things were being over-maintained for what they actually needed. So that was that's an example where you've, you know, reduced some time, maybe saved some cost, or just freed up time to work on something that's more critical. At another project, they looked at the SF6 breaker disconnect system, and that was one where they'd been experiencing failures, and they'd seen a degradation in that equipment. And what they realized was there was a previous cost-saving measure that was used where they eliminated some tasks, and they determined that that particular task was very important for the reliability of the assets. So in that case, that RCM study determined you actually need to increase your wrench time by 46%. So while, you know, sometimes you might see people saying, you know, RCM is saving you a bunch of money, in this case, it is actually increasing the amount of time spent on the asset, but improving reliability, which can save you money on, you know, the loss generation side if you were to have too many forced outages by not maintaining things properly. So there's multiple ways that you see benefits from these. Finally, the governor system. This one was kind of an interesting one too. Similar to the unwatering and drainage pump system, they did identify that there were some kind of redundant tasks being performed, but the other thing that was interesting was just due to the level of redundancy in the system, they determined they could remove about 58% of the job tasks in that plan because there's just so many levels of redundancy that you don't need to maintain that particular system at that plant as much as they were doing. They determined they were able to, you know, take on a little bit more risk and do things a little bit more reactively, technically, if it came down to it, because there's just redundancy in the system. So some interesting takeaways from that. And, you know, it's something that the Corps is interested in expanding across more asset types as we kind of move along. Okay, next slide. So the last one I'll talk about briefly is the detection, monitoring, and analysis of cavitation for turbines. So this is one partnered with GE Vernova and Bureau of Reclamation, and this is really just kind of looking at trying to understand through machine condition monitoring and instrumentation where rough zones are for turbines and identify, where you can reliably operate those units without causing damage and cavitation. And so it's kind of validating existing understanding of where those are, or really refining where they should actually be. So that can help, prevent cavitation damage, but also if the existing understanding of where those cavitation limits are, were maybe wrong, or maybe we can now operate in a broader operating range, for example, that could improve some operational flexibility as well. So there's both a reduction in cavitation costs that could happen, but also possibly increase operating range potentially too. Just better understanding where that is. Let's go to the next slide. Just some quick information on how that's kind of progressing, as there was a number of different instruments and instrumentation that was tested. So there were acoustic emission sensors, there were accelerometers, and some sound level microphones. And the initial findings were that the AE sensors provided the best data that you could correlate to cavitation. But all the sensors together can help identify where sort of those low efficiency operating conditions might be. So there's more work ongoing there, but so far there is an active cavitation monitoring system in place via those acoustic emission sensors, and those proved to be provide the best data for us at that point. So that was all of those that we were going to chat about today. So we can definitely start to take questions if you have any for either of us.
Super. Well, thank you so much, Nell and Gordon. That was a great overview. I'm sure it's going to generate a lot of great discussion and Q&A here. So just taking it from the top, Jeff Leahy dropped in 2 questions. Nell or Gordon, I think you addressed the second one. We'll revisit it, but back up to the top. And Jeff, feel free to jump in here, but I'll just read your question out. So this relates to, I guess, managing through October and the shutdown, and not sure how big of an impact that had on Bonneville, but Jeff writes, was a group SME meeting held this past October during the shutdown? If not, will it be rescheduled? So
Yeah, we are on a different cadence than normal because of the shutdown and the administration change. So my presentation was based kind of on what we were doing, what we traditionally do year over year. But we had those meetings at the beginning of last fiscal year 25, and then we continued to use those inputs, and then got some additional executive inputs for fiscal year 26. And for fiscal year 26, we just have a standalone 1-year research priorities, which is also atypical. Typically, they align with the rate period. Mm-hmm.
Great. And then just on the second one, I believe Gordon might have covered it, but in terms of average annual budget for these activities, what is the average project size and funding? Nell, you might have said 3 to 500,000 per project.
TI typically for the partner projects with federal partners, we go anywhere from 25,000 to about 200,000, depending on the project length and scope. But that's about our range.
Got it. And any color from overall annual budget for TNI?
It's a little over 2 million, and then we have some of the budget that's obligated to different partners. So certain parts of it have to go to certain research partners contractually.
Great. Okay, super. Okay, switching gears. This next one comes from Jay Mearns at Pacific Gas and Electric. Is BPA able to use machine rating curves to validate the SCE-TOM ensemble models?
Yeah, and that was the one that I was kind of mentioning earlier, and just rethinking through the question there. The SCE-TOM is built up from the individual curves for the turbines themselves. So that's how, when it's building the overall plant power hill, it is doing so by looking at each individual unit and where it can individually operate. Hopefully that answers that question. And then, like I said, oh, sorry, go ahead.
Yeah, the idea is more, the backcast, looking at your ensemble results and then comparing that to historic operation. And you pretty much answered that in the first response. So I appreciate you taking the time to consider that.
Okay, thanks.
Super. All right. Next one here from Vincent Bryan. Is spill for fish passage taken into account in the SCE-TOM model?
Yeah, so that's one that is very relevant, because we might need to be, we want to try to improve how we're doing that, because it gets harder and harder to model, it seems like. When we first started doing this, the fish passage spill requirements were simpler. They were, generally just a standard KCFS or a percent of the river flow, right? So that's an easy number to plug into a model. With spill to gas cap, that's a harder number to pin down, because it's really dependent on a lot of different variables, upstream conditions, different how many units are running at the plant, all that kind of stuff. So that's one that we're actually talking about right now on, how can we improve that so that we're really understanding when we're looking forward the level of spill that is required for fish at those plants. So we do incorporate that. It's just it's something that has become more difficult to model.
Understood. All right. So we'll throw it open now for some additional Q&A and non-scripted and discussion. So I've got one. So relative to how these initiatives are leveraged, let's start within the FCRPS. So if you're partnering with HDC, for example, on SCE-TOM, would you be at liberty, not at liberty, but working with reclamation, for example? Would you be in position to take something that works for core facilities and bring that to the attention of the reclamation plants within the FCRPS, for example? Like, can you cross-pollinate?
Yeah, and we've done that with Grand Coulee, actually. So we actually had a project, not a TI project, but obviously the TI stuff has benefited the development of SCE-TOM. But there was a project between BPA, the Corps, and Reclamation where we did develop a SCE-TOM, I guess you would say, for Grand Coulee. So we have used it there to analyze investments at that plant. So yeah, it's possible.
Yeah. And what about beyond the FCRPS? So for example, if you've got something that really works well for core facilities within the FCRPS, would they kind of take that nationwide if it really worked? And what role would you play in helping that happen?
They've used it outside of the FCRPS at core, outside of the Pacific Northwest at core facilities as well. For those plants, I think they're generally looking more at specific turbine design, and they don't use it as much for the investment plan as what we do. But I think they have started to do a bit more of that. And I think originally some of the idea for SCE-TOM started outside of the FCRPS. It was just for like a turbine sizing study, I think. And then at some point we realized that we could use it for this application, and that's quickly become the main application, at least in the FCRPS anyway.
Interesting. All right. Questions, thoughts from the group? Discussion topics? So Nell, I've got one for you. So looking as best you can, given everything that's going on, looking into the not too distant future, let's say short to medium term future, any color you can share on some new interesting hydro related R&D projects that's got you excited?
Yeah, so we're continuing the RCM pilot for this year, and then we're also continuing the work on the SCE TOM model. We're continuing the cavitation work with reclamation. So the 3 projects that were presented on, we have funded last year and continue to fund this year. Then we also have a project in the works with the Army Corps of Engineers for an AI tool based on the government approved Julix tool to look at data and then provide facility specific responses based on the inputs from the Army Corps of Engineers. So that's a project that we're scoping right now. And then we've had some initial meetings with PNNL and the Army Corps of Engineers to talk about repurposing the test stand that they used for thrust bearing tests previously to look at different components on the turbine. So that we haven't scoped that yet, but that is kind of coming up this year. Also, our budget is on an annual cycle, and last year, just because of shutdowns and the DRP and various different things, a lot of our projects didn't get off the ground. So a lot of those got pushed forward to this year. But I work fairly closely with my counterpart at Reclamation and the Army Corps of Engineers. So we share our R&D initiatives for the fiscal year every year. And then I work with Gordon and George's group to kind of prioritize those and make sure that we're supporting their efforts where we see it's most beneficial for BPA.
Awesome. Thank you for that added color. Another couple questions here from James Lussman, Seattle City Light. Can you talk a little more about the acoustic emissions testing? Whose equipment is it? How many units take advantage? What do the outputs look like? And is that taken at the draft tube level?
Gordon, I think Mike is on the call. I asked Mike Rao to come, so if we got additional questions on the reclamation work, he might be able to help with that. So I just wanted to preface the answer with that. We might have to popcorn to Mike.
Sure.
Okay.
So, hey guys, if you don't mind if I talk
please.
a little bit. Hey, I'm Mike Rao. I'm a mechanical engineer at the Reclamation's Technical Service Center in Denver. Anyway, yeah, we've partnered with BPA on this cavitation monitoring project for the last 2 years, and it'll continue into at least the next year. It's a sort of a longer running project, partnered with GE and our research office. I know Jim Dahan and Aaron Fork are on the call from Reclamation too. But yeah, James, to answer your question, those AE sensors are Kistler brand. We utilize that on units G20 and G24 at Washington Powerhouse at Grand Coulee. Honestly, I guess the most valuable data that we've gotten from those acoustic emission sensors comes from those installed on the Wicked stems and then the draft tube liners. And the output really is just sound intensity. It's, the frequency range that they pick up, I think, is between 100 and 900 kilohertz for the most recently installed sensors we've got on the units. So it's, I guess, a lot higher than you'd be able to detect otherwise. But does that answer your question? James? I guess I should probably say what we're trying to pick up is cavitation intensity.
So he's chatting. So you map intensity to risk of cavitation?
Sound intensity.
Yeah, exactly. We're trying to map, I guess, sound intensity output in that high frequency range to tell us where that cavitation is occurring during operation.
Are you looking at runner buckets, or are you looking at Wicked stems, Wicked blades?
It's either. Yes. So it's one's installed on a Wicked stem, in the turbine pit. And then we've got sensors installed on the draft tube liner near the doors, just because that's about as close as we can get to where the cavitation of the runner is actually occurring during operation.
Awesome. All right.
Thank you.
Thanks, Michael.
Sure. Yeah, thank you.
All right. Other thoughts, questions? A few seconds. Let folks get off of mute if they've got something.
Just a question, and Gordon and Neil, this may go back a ways, but I know at one point there was some detection work that was being investigated for being able to record blade angle. So this was a time domain sensing system using fiber optics for blade pitch angle to assess where that 1% efficiency would be arrived at. And as a part of that, is there any thought about incorporating any light frequency measurements from the water column? And specifically what I'm thinking about, we observed some photoluminescence in a very high cavitation region for one of our hydro facilities. And that represented an area where we were getting some UVC and visible light signature off of the water as a result of the cavitation severity. And so I wondered if that, would represent an opportunity in the discharge column to potentially instrument that for a higher frequency content.
Who was that question for? Sorry.
I was gonna say,
That's not one I can answer. I'm sorry
Gordon
on
or
that
Mike,
one.
maybe you can try for that one. Sorry.
This is Mike again. I don't know if I have a good answer for that question on our end, to be honest.
Yeah, it's a little bit outside of normal, but it does represent an area that we've observed a fairly significant correlation with those higher levels of cavitation energy. And it just represented one additional signal that could potentially be correlated for the magnitude of that energy, that damaging energy. So anyway, we can take that offline.
Awesome. Thanks, Jay. All right. Last thoughts, questions? All right. Well, thanks once again, Nell and Gordon, for putting this together. And thanks to the audience here. Very good turnout today. Much appreciated. Like I said, great presentation, great Q&A, some good discussion. We'll leave it there, and we'll see you all again soon. And again, this is being recorded. We'll have the video posted in the OpEx video library, hopefully within the next week. Have a great day. Have a great rest of the week.
Thanks, Chris.
Thanks, Chris.
Thank you.